The last thing I'm talking about star evolution is the ways that a binary system, a companion star system, can affect the normal stellar evolution tracks that I've been talking about. There are a few ways this can happen. For instance, if you have two neutron stars orbiting each other in a binary system, it's been known that sometimes they might, collide with each other and fuse into a black hole. That's not particularly interesting. I mean, that is interesting, but I don't have a lot to say about that. What I do have a lot to say about is this one particular case where you have a white dwarf and a normal main sequence star, or maybe a giant, in a binary system, and the white dwarf is able to siphon mass off of the its partner over time. Now, white dwarfs are kind of, in a lot of ways, defined by electron degeneracy pressure and the fact that they aren't strong enough to beat it, right? If they were strong enough to beat it, they'd turn into a neutron star. So, since white dwarfs have to be held up by electron degeneracy pressure, it's possible to figure out what the most massive possible white dwarf is. And it's been determined that the most massive a white dwarf can be is 1.4 solar masses. This is called the Chandrasekhar limit because a guy named Chandrasekhar derived it. So yeah, this is it. This is the maximum mass that a white dwarf can be. But what if you have a white dwarf and it's orbiting another star, right, in a binary system, and it's stealing some of that other star's mass, right? Over time, the white dwarf's mass would increase, and maybe, eventually it will pass the Chandrasekhar limit. It'll steal enough mass to get past that magic number. Well, what happens then? It goes supernova. It goes supernova, right? But here's the cool thing about when a white dwarf goes supernova like this. Because the white dwarf always goes supernova upon crossing the Chandrasekhar limit, that means that every supernova that happens for this reason happens under the same situation. The star has the same mass when the supernova happens. And so that means that every supernova caused by this situation is going to be the same brightness. We call these supernovas that are caused by this situation of a white dwarf stealing mass from a partner and passing the Chandrasekhar limit type 1a supernova. And the fact that they're always the same brightness is very useful, because if we see a type 1a supernova, which we can tell from distinctive spectral traits that they have, well, now we know how bright it should be, and we can compare that with how bright it is, and figure out how far away that supernova is. So that's a really useful method of figuring out distances in astronomy. But yeah. So what about these types? I'll go over that quickly. Supernova are broadly categorized into type 1 and type 2. Those have to do with spectral features. I'm not going to get into that. Basically, type 1 has 1A, 1B, and 1C. 1As are caused by this situation of the white dwarf stealing mass from a partner. But type 1B and C and all of the type 2s are caused by core collapses, the same kind of processes that end up making black holes and neutron stars. So, those are a quick rundown of the types of supernova. And I think that about covers it for this week. Go ahead and do the homework assignment.